So, we have learned how to design that short columns. Now, today we shall learn how to design slender columns, or we call it long columns, and this is our lecture number 29, design of RC reinforced concrete slender columns. But before I start this lecture, I shall give one correction. Last class what we have done the design of that say due to torsion. By mistake we have omitted that 0.87. In both cases, here also it should be 0.87. Please take care this 0.87, and here also there should be one multiplication 0.87. That we have forgotten to take it, but we have, when we have given the sketch, the design procedure, there we have written 0.87, but while calculation of the problem, there we have omitted this value 0.87. So, we are not doing the calculation, but anyway you check it, your calculation with this 0.87. That means your shear stress, sorry, area of steel, it will be more here, that. So, you will get that more reinforcement. So, accordingly you change your calculation, the rest of the calculation of that problem which we have done in the last class. Okay. Now, come to the say design of RC slender columns. Before that we should know why we really need it. That means we have to know the effective length or effective height, whatever you call it. Effective length of column, that is dependent, we have, if we take a plan or cross section, this is the plan x and y. So, we have the two effective length LEX and also LEY, because depending on the, it is dependent on that L and the condition of the boundary condition at the top and the boundary condition at the bottom. So, you will get two effective length, not the one effective length for the one column. Say like beam, you will have only one effective length or effective span, but here you may get two different along x and along y. For a we have done so far that buckling of columns, that buckling or stability, buckling of columns that you have done, and it is based on the same principle. That means here what is happening in this case, there is certain say deflection, or let us say E, and this is your deflected shape. We are not talking any eccentricity at the top, we are talking as if the from the center line of the column that your loads are acting, even then there could be say some kind of deflection, that buckling of the column. But whereas in the short column, that whatever we have designed so far, we are assuming that there is no deflection due to the load. That means there is no buckling of columns. So, whatever moments or whatever axial forces developed on that column, that is due to applied load only. But here, in addition to that load, that analysis, whatever you have got it, in addition to that, you have to take care certain load or certain moment due to this deflected shape. And so, we know that according to IS 456, that effective length of the columns divided by the lateral dimension that means L by D or L by B then if it is greater than 12, then we shall call it as a long column or slender column. So, this is our long column and this is our short column. Now, what we have to find out, we have already done that from the IS 456, the table where it is given, but different boundary condition, the different support condition say fixed, and there is no displacement, there is no rotation, that is fixed, or that is restrained, say from against rotation, against displacement, like that there are so many conditions we have found in the table, and then we can get that effective length factor. That means the unsupported length multiplied by that factor will get the effective length. There is one more case, and that I think we should know, that is for the frame structure. Let us say, let us take a specific problem, or for frame structure we can consider. We are taking a frame and let us say that means this is a part of one building frame. We are taking a part of it and about only in one plane. It could be other way also, but we are taking only one plane. So, if we take this one, let us say the column stiffness of the top, that is KCU, column stiffness at the lower one, that is say KCL. This is the actual column which we are considering, that we have to find out the effective length of this column. We are interested to find out the effective length of this column, but we are having certain percent at the top, certain percent at the bottom, because we have taken a part of the building frame and about one plane, in one plane only. The other plane also perpendicular direction, that also there is another one, but we are not taking care say right now, just we are giving one example. Let us say there is a one beam here KB1, another beam say KB2, here say KB3, another beam, and here say KB4. So, this is your top beams and this is your bottom beams. What we do? We have to find out the effective length. Here this is not the case which we have done it, which we have already done it, that is according to your say table. I think that table I think we can refer, we can give you. We have done it so far in Annex E, and Annex E, that is your table 28. If you remember the table 28, there are 1, 2, 3, 4, 5, 6, 7. There are 7 cases, and one of the case I think I should tell you, just simply if you remember, just to remind you, effectively held in position and restrained against rotation in both ends. That means the case where we have effectively held in position and restrained against rotation at the top as well as at the bottom, that is one of the cases. So, for this case, if we find out the effective length, theoretically that is 0.5 L, but here the code says that you take it 0.65 L. So, that is a case where it is clearly mentioned, but when you are talking say building frame which you have to design, for that you have to find out the effective length, and which will not fall out of those say 7 cases. So, how shall we find out that one? We have to find out that according to this stiffness. So, you have to find out the stiffness, and accordingly we have to that calculate that your effective length. So, there are 2 parameters we get it, that is one is called beta 1, which will be equal to Kc, Kc is the column stiffness, plus KCU, that is the top one, that means this is the at this junction we are talking at the top, Kc by KCU plus Kc plus Kcu plus, for this case it should be summation of K, say let us say Bt, T means here 1 2. So, summation of all the top beams. So, that means here we are getting certain kind of say one parameter, that factor, that one will give me that parameter which what is the relative stiffness of this one, that percentage of this one, that we shall find out, and that is we are talking say beta 1 for top joint. Similarly, we shall get beta 2, and that beta 2 will be equal to again Kc, the column which you are considering, plus Kcl divided by Kc plus Kcl plus summation of Kbl, that means for the bottom or the lower one. So, we shall get beta 1 and beta 2. Now, our code gives the two tables from where we can find out that effective length. So, this beta 1 and beta 2, our code gives the two tables, and that we shall get it here. So, this is your one table, and you will get it in Annex E. Annex E, this table figure 26, effective length ratios for a column in a frame with no sway. If the frame has no sway, in that case I shall take one parameter beta 1. Please note here it is fixed. This is your fixed position, and in that case if it is fixed, both ends fixed, then we shall get 0.5. And similarly that beta 1 starting from 0 to say hinged position, that is 1. So, beta 1 can have the value from 0 to 1. Similarly, the other end also 0 to 1. So, we have these two values, that means already we have calculated one parameter beta 1, another beta 2, and according to that we shall find out that value. So, if it is say 0 0, that means 0.5, that is the case for fixed end condition. And the other condition, when both ends fixed hinged, that means it will be the effective length will be same as the length of the column. So, that is 1. So, we are getting it here 1. So, we shall get different values, and we can find out that different values here say 0.55, 0.575 or whatever it is we are getting, that value we can find out. Okay. So, this is the one we shall get it. So, what we shall do it here then? Let me write down that few steps to find out. To determine beta 1 and beta 2, use the substitute frame method. What is that? We have substitute frame method. It means we have taken a part of the building frame. We are not taking the, we are taking a part of that. That means you are taking a column and about x axis say. So, you take that plane, and in that plane you go only top one column and bottom one column, and similarly right and left one beam each side. The way we have done it here, that means this is a building frame. We are interested to find out the effective length of this column. So, what we are doing, we are going one floor up, one floor down, and we are going one say panel this side, another panel this side. That means one beam in the left, one beam in the right. Similarly, for the bottom also. So, that means when we are doing that, that is called your say substitute frame. So, that case we take it. That means instead of having say your, either we can do it say moment distribution method for your analysis, we do it, or say slope deflection method, or say just simply say continuous beam for your analysis I am talking. Similarly, you can take a substitute frame method. That means there you take it say only say your beam only we shall take it, and one floor up, one floor down for your columns. We are not taking the full building one the way we do it in the computer analysis, we do it, but we generally do not do that way in say manual calculation. Number 2, for braced frames, no sway, the beam stiffness should be taken as K beam equal to I by 2L. For braced frame, that means there is no sway, we shall take it 0.5 I by L. Number 3, for unbraced frames, the beam stiffness should be taken as KB equal to 3 by 4 I by L by 2 equal to 1.5 I by L. So, this is your case, we take it. So, these are the cases we shall take it, that whatever the beam stiffness KB and this one for the unbraced one, that we shall take it, this value 0.5 I by L and 1.5 I by L, that we shall take it. I think it is better that if we solve one problem, then it will be clear. So, let us take one example. So, let us take first this is the plan of a building, say, just a simple one, plan and let us take the dimensions are 6 meter, 6 meter, this side, this is also say 6 meter, 6 meter, and we have these beams, let us say 250 by 400. Okay, these beams, these, all these beams are 250 by 400, whereas the other side, say let us take, due to loading maybe, that is coming as say to 300 by 500, other side, and columns 300 by 300. Let us say the building frame so let us take this building frame. This is a 4 meter height, this is the elevation, this is also 4 meter, 4 meter, 4.5 meter, and whatever it is that your foundation. Let us say we are interested to find out the, instead of having that or all other cases, let us take say only this case. That means this column, say we are interested to find out the effective length of the this column. That means each of them we have to find out. It will be something 4 meter multiplied with some that factor that we have to find out. So, this is a 4-storied building. So, we have to find out that this one, that means not other cases, that means here whatever we have this beam and this beam and the column. So, we shall find out the effective length of each column. First you find out unsupported length, that is equal to full length minus beam depth. So, we shall get it roof to first floor, third floor. Roof, third, second, first, ground. So, we are having this floor. So, roof to third floor means this one, third floor to second floor means this one, second floor to first floor means this one, and first floor to ground floor means this one. So, we are having those 1, 2, 3, 4 columns, and effective length will be different. So, we can have say XX, that one will be here 4000 minus the beam depth, that is we are given 400, and which comes as 3500. In Y it will be 4000 minus we have taken, it will be 3600, and this one will be 500. So, 3500. Then we are having say between third and second the same one. So, 3600, and here we will have 4000 minus 500, again the same one 3500. Now, second and first the same one, this is in millimeter. So, 3500, and first to ground floor we will have 4500, that is the one we have taken, please note 4500. The first floor, that one it is little higher. So, 4500 minus 400, so which comes as 4100, 500 minus 500, which comes as 4000. This is your unsupported length. What about your that say I, second moment of area, section properties? So, there are, we can take in this case, we can find out that one column, that is 300 by 300 cube by 12, that is the one that moment of inertia or second moment area, and this one comes as So, we can write down this one as say 675 into 10 to the power 6. What about your L? The L we shall get it here. So, L we have 4000 and I by L, this one, let us say I by L we can multiply it with say 10 to the power 3, just I am taking it out 10 to the power 3, that if we take it out we shall get it here, this is your I, L is this much, that 4000, and so I by L, that one is coming as 168.75. So, 168.75 into 10 to the power 3, that we shall get it. Now, there is one more column according to say your length, the section is same, but length is different. So, we shall get it 300 equal to 675 into 10 to the power 6, L is here 4500 and we get it here 150, that means 150 into 10 to the power 3, that we shall get it. C, that is your beam, say XX in the XX line, and that one 250 into 400 cube by 12, that is along one axis, that is 250 into 400, 250 the width and 400 the overall depth, and this one comes as 1333 into 10 to the power 6, length is here 6000, 6 meter, and we get it here 222 into 10 to the power 3. Beam YY, that means along YY, that is 300 into 500 cube by 12 equal to 3125, and length same 6000, and we get it 261. So, 261 into 10 to the power 3. If we take it this one as a say braced frame, the frame is braced, we are taking that one. So, braced frame, then what should be our correction? The correction will be here, that 0.5 times I by L into say 10 to the power 3, the same one I by L into 10 to the power 3, this is L. So, for columns there is no change, it will be same as 168, let me write down here 168.75, for columns there is no change, for this column also there is no change, here it will be 111, that means half of this one, that will be 111. I think I have done a mistake here, let me check it here. So, 3125 divided by 6000, okay, so which comes as 521, sorry, this one is 521. So, half of that 521 into 0.5, 261 say, yes, this 261 will come here. So, this is your that values we shall take it, that means KB 111, KB here 261, the column that one there is no change 150, for column that another column 168.75. Okay. So, this is your section properties. Now, we can find out the stiffness, ratio of the stiffness we can find out at different joints. That means, ratio of stiffness means the column stiffness and the overall stiffness of that particular junction. So, top one is roof 168.75 divided by 168.75 plus 2 into 111, that is the beam, which comes as 0.43, that is XX. Please note, we have taken that one here 168.75, 168.75, and and that beam we are having here along x we are talking, so 2 into 1 1 1. So, one case we are considering here. I think I should write down here that one frame, that it will be clear. So, we are interested here, to find out, say, this one. When you are talking this one, then this is your roof, this is your third, second, first, similarly it will go down ground. So, at this level we are having only this column, but when we shall take this one, then we are having this column as well as this column. So, for roof in XX we are having, and we are taking this one only, these two. Similarly, for YY we shall take it as 168.75 divided by 168.75 plus 2 into 261, which comes as 0.24. So, it will be other way, the normal to that one. That means we are taking that. Okay, let me draw the plan, I think then it will be clear. So, we are talking the column position at this level. So, when you are talking the roof one, then we shall take along XX, that means this one only, this frame. We shall take this frame, but when we shall take, say, along YY, then we shall take the other frame. So, that is what we are doing. So, number 3 it will be, but when you are talking this one, then this column as well as this column, to 2 into 168.75 divided by 2 times, I think I can write down both, plus 111. That means, you are having the beams, 2 beams and top and bottom columns, which is coming as a 0.60. Similarly, here also 2 into 168.75 divided by 168.75 plus 261, which comes as 0.39. So, similarly, we can come down, say, 2 also, 2, 1, all of them we can do it. The similar fashion we can do it. So, let us find out for 2 at this level, like that, let us find out. Yes. So, we are taking, say, 2 into 168.75 means this is 168.75, this is 168.75. For what about for beams? Because we are taking along XX, we are taking for along XX, similarly for YY. So, Y will be the other way. So, for XX means here 168.75 I have taken this one, and at bottom 111, 111. That means, for this beam that we have got it 1. So, that is why you have multiplied with 2, and that we will get 0.60, and similarly here also. So, same fashion I think we can complete the other one also. So, number 2, 2 into 168.75 divided by 2, 168.75 plus 111, it will be same, that is 0.60, that is XX. Similarly, for YY, 2 into 168.75 divided by 168.75 plus 261 equal to 0.39. Now, 1, that will be 168.75 plus 150, because the ground floor to first floor, that column height is different. So, that is why you are getting different one. So, 168.75 plus 150, top and bottom different, plus 2 into 111, which comes as very less change, but anyway 0.59. The other one 168.75 plus 150 along YY you are talking. So, 168.75 plus 150 plus 2 into 261, which comes as 0.38. For the basement or the ground basement, we can talk the bottom, that we take it beta equal to 1, here also beta equal to 1, because we are not, why you are taking this one, because that foundation not designed for bending, that means as if it is hinged one. So, that is why you are taking that beta equal to 1. So, if we take these cases, that means for all the cases we have got it, the different values we have got it, and we can find out now the effective length ratio. Yes, we have taken the, for the bottom we have taken, yes, basement, or yes, okay, let us call it ground, say, yes. So we can take that particular point because we are not transferring any load to the foundation, then not for bending, only we are transferring axial load. That means in other way you can consider it as a hinged condition, and that is why you are taking beta equal to 1. If you are interested and if you design for that one, say for bending, then you have to accordingly you have to calculate that beta for taking, say, foundation depth, say 1.2 or 1 meter, whatever you have provided, on the basis of that you have to find out. But most of the cases we take beta equal to 1. So, for different story, say R3, beta 1 and beta 2, we are talking, say, only XX, say. So, we can get beta 1 and beta 2, R3, that is given, say 0.43, we have got it one case, another 1.60, then 3, 2, both 0.60, 0.60, 2, 1, again 0.60, 0.59, and 1 ground, that is your, say 0.59, 1.0. These are the different values for top and bottom. So, beta 1 and beta 2 we have got it, for top and bottom we have got it, say these values we have got it. So, what about the ratio then? Then the factor we have to find out, that factor, the ratio that we have to find out, where from we shall get it. We have two cases. One is that one, say no sway, here this is the case of, say, no sway. I think I can show you that at least the next one. We are having another one, that figure 27, where we are having that one, say without restraint against sway, that means we are having sway. For that case you will find out the ratio is getting that more than 1, that 1, and it is going up to, say, infinite. So, from 0 to, say 1, but anyway this is another case when we are having the sway, but here the case we have considered, that is your, say without sway, there is no sway. So, we shall go to the previous one, that is your figure 26. So, what we do it here, we have got the top one, say beta 1 0.43, beta 2 say 0.6. So, what we can do, so beta 1 say 0.43, it will be somewhere here, please note it will be somewhere here along this line, and beta 2 that is say 0.6, so it will be somewhere here. So, wherever it will cut, then we shall get, there are different lines. So, from there we can get the ratio. So, that figure, from this figure 26, so we have to select the figure which case you are considering, whether you are considering, say without sway or with sway. If it is without sway, then we shall take figure 26, if it is with sway, then figure 27. So, in our case we have considered this one, say without sway. So, in that case, that you will find out that all the values are coming less than 1. So, 0.43 and 0.46, for that the ratio from the table, sorry, figure 26 IS 456 2000, that is our reference. In that case, taking this beta 1 and beta 2 different values, we shall get, this is your, say 0.6875, then 0.733, the next one, say 0.73, and this one, say 0.85. So, we have got these values. What about the L0? So, L0 that we have got it, let us write down. So, 3600, this is also 3600, and 4100. So, these are the values we have got it here, and now we can find out the effective length. So, LE equal to so 2475.733 into 3600. So, 2639.73 into 3600, 2628 4100.85. So 3485. So we can find out this effective length, and we can find out that divided by the lateral dimension, we can find out that factor which is coming, say value that L by D or LE by D or LE by say B. We can find out that values, whether it is coming less than, if it comes less than 12, then we have to design it as a short column, and if it is greater than, then it will be treated as a long column. But whatever way we consider here, all the cases it seems it has come that because D equal to, say you have to say 300, so we can find out here. So one of the cases I can say 3485, that is the maximum one, and divided by 300, which is coming as say 11.61, so less than 12. But if it is say 250, 3485 divided by 250, in that case it is coming 13.94. That if we take that same case, say your say 250, then it will come say greater than 12. Then in that case you have to design it as a that long column. So here also we can take the dimension, that is important, whether you have to design it as a long column or short column, that we have to find out according to this. So this is your that for frame structures, braced or unbraced. For that case we do it, and we find out we calculate the your say effective length, and then the rest of the procedure is same. That means if we can find out the effective length, then we can find out for long column or short column design we can do it. Now what is the difference that in the long column design? So far we have done that effective length only. Now what about the long column, the design, how does it affect? Here also what we do, I think I should go to the reference of the code. So that is given in clause 39.7, page 71, IS 456/2000. So in this case, what will happen here, IS 456/2000, in this case what we shall do, that it says that there is a additional moment. So we shall take the additional moment, and those are say, let us say MAX will be equal to PU D divided by 2000 multiplied by LEX by D whole square. So we shall get it, we know PU is the applied load. So that means here this value, whatever we are getting here, D by 2000, this value, that is nothing but the E or eccentricity, I can say. Indirectly we are calculating the eccentricity along X, and similarly we are calculating eccentricity along Y, which means PU times B divided by 2000 multiplied by LEY by B. So where PU, that axial load on the member, LEX effective length in respect of the major axis, LEY effective length in respect of the minor axis, and d is the depth, and that one say you can consider depth, and the other one is the width of the member. So, these are the all the cases. So, that means here we can say d by 2000 times Lex by d whole square, that is nothing but the eccentricity, and if we take in other way we can say as if that we are getting this value. This value we are getting, that will from the buckling point of view you are getting, and if you consider that from the critical load, if we take the critical load, what is the buckling one, that first mode of buckling, second mode of buckling, like that, from there you can find out that eccentricity, and accordingly we can calculate. But our code says this one, that for a particular case you can say that your value, whether if it is hinge condition, then your value will be different. If it is say one end fixed, other end say hinge, the value will be different. But here our code gives in this fashion, so that we can take say almost say equal value in all the cases, that maximum possible cases, that the we consider this one as a safe design, that we shall take it. Okay. Now, what we shall do it here, just to give you the design procedure, I think that we shall make a design procedure here. Here is a column say, and which is valid for both axes. One case say we are having here say M1, another one say we are having say M2. M1, M2, that means you will get that from your analysis, you will get that your say moments at the top and moments at the bottom. So, you will get that moment at the top and moment at the bottom, and it will happen like this. It may happen say in this fashion also, it may happen. So, we have to find out the intermediate bending moment. We shall find out the intermediate bending moment here, and that intermediate bending moment, what we take it, that is say Mi will be equal to say 0.4 M1 plus 0.6 M2. This is the value we have to take it, that means at this point we shall take it say 40% of this and 60% of that, we shall find out that one. After getting this, and in addition to that we shall get that additional moment. So, that means this one you are getting from your analysis, and now if it is a long column or slender column, so you will get the additional moment, whatever that Pu is acting here, Pu, that is only you will get it only 1. So, from that Pu you will find out, I can say eccentricity will be equal to d by 2000 times say Lex by d, one case, or Le by d, I can consider this one. So, this I can get it, let us say Ex. Similarly, say Ey will be equal to b by 2000 multiplied by Ley by b whole square. So, we shall get Ex and Ey, the different values, and after getting this, similarly I can get it M1 means x about along x, M2 along y along x. So, similarly from the other axis we shall also get it. So, after getting this one, there are few cases we consider. Number 1, let us say Mi equal to M2, if we consider the maximum. So, Mi equal to say M2, that is one case. Number 2, Mi equal to M1 plus Ma by 2. M1 means the top one, say that minimum one out of M1 and M2, and this Ma by 2. Ma by 2 we are getting out of this eccentricity. Number 3, Mi equal to M1 plus say Ma, and number 4, Mi equal to M minimum. So, what is M minimum? M minimum we can get it from that E minimum, which equal to L0 by 500 plus D by 30. That please note that already we have used it. So, L0 by 500 plus D by 30. So, from there I shall get E minimum. So, M min will be equal to PU times E min. So, we are getting 4 cases. That means, if we know M1, M2, so I can find out Mi the intermediate moment, that one, say just simply take the maximum one. Mi equal to M1 plus Ma by 2, that additional moment whatever you are getting due to this, say your slenderness, that ultra multiplied by Ex when you are talking say along X. So, we are getting say Pu times Ex or Pu times Y. The other one Mi equal to M1 plus Ma, and the fourth one Mi equal to M minimum, which you are getting from the eccentricity point of view. Yes. That is the one we are getting this value, we are getting it here. That means, if we know M1 here and that M2 here, then we can find out this value, that we can get it here. Okay. Now the thing is, out of that we have to take the greatest one, greatest out of these 4, and that is your that moment we shall take it. That means, we are taking this moment, that what is the moment we are getting here, the maximum one out of this 4 we are taking, and then rest of the thing we shall do it according to the one design whatever we have done it. I just say using say that SP16, that we can find out the design. Okay. But only thing that in slenderness column, slender column, what you have to do, you have to find out that moment how much it is coming. So, applied load and the additional moment due to this eccentricity. So, our code gives only this formula from where we can get that additional moment, and that additional moment has to be applied like this. So, out of that we shall get the greatest one, and along X, similarly along Y we shall do the design. Okay. And that is all.